Let us discuss some force field in molecular mechanics. First of all, we have to study what is a force field. We know that molecular mechanics uses a mechanical model of a molecule to find its minimum geometry using simple equations of the classical mechanics. The form of the mathematical expression for the energy and the parameters on it constitute a particular force field. Hence, molecular mechanics methods are sometimes called force field methods. The term arises because the negative of the first derivative of the potential energy of a particle with respect to displacement along some direction is the force on the particle. The force field energy is written as the sum of the terms, each describing the energy required for distorting a molecule in a specific fashion. Therefore, the total force field energy can be written as the sum of E stretch, E bend, E torsional, E van der Waal, E electronic plus E cross. The process of finding the parameters corresponding to E stretch, E bend, E torsion, E non-bounded and E cross is called parameterizing or parameterizing the force field. Here E stretch is the energy function for stretching a bond between two atoms. E bend is the energy required for bending an angle. E torse that is the torsional energy for rotation around a bond. E VW and E EL represent the non-bonded atom interactions, and E cross that describes the coupling among the first three atoms. The set of molecules used for this is called a training set. Let us discuss some commonly available force field which are used in different types of force field methods, that is in different molecular mechanics. The first one is MM2, MM3 and MM4. The molecular mechanics family of force field, that is MM1, MM2, MM3 and MM4 are the general purpose organic force field. The force field can identify sp, sp2 and sp3 hybridized carbon atoms, organic intermediates such as free radicals and carbocations, the carbonyl functional group, cyclohydrocarbons such as cyclopropane, cyclopropene, etc. The molecular mechanics family was parameterized to fit the values obtained through electron diffraction, which provide mean distance between the atoms averaged over vibrational motion at room temperature. The bond stretching potential is represented by the classical Hooke's law expression, that is, it is a lengthy expression. These force field use 5 to 6 valence terms, one of which is an electrostatic term and 1 to 9 cross terms. The MM3 method is probably one of the most accurate ways of modeling hydrocarbons. Next is AMBER. AMBER is the assisted model building with energy refinement. It is the name for both a force field and a molecular mechanics program. It was parameterized specifically for proteins and nucleic acid. AMBER uses only 5 bonding and non-bonding terms along with a sophisticated electrostatic treatment. No cross terms are included here. Results are very good for proteins and nucleic acid but can be somewhat erratic for other systems. It should be noted that AMBER employs a united atom force field and use improper torsion terms to maintain stereochemistry at chiral centers. AMBER also includes a hydrogen bond term which augments the value of hydrogen bond energy derived from dipole-dipole interactions of the donor-acceptor groups. This result in significant additional speed in calculations based on amper compared to the other force field. It uses general torsion parameters. Next is CHAM, chemistry at Harvard. Macromolecular mechanics is the name for both force field and program that is already mentioned. Next is Merck molecular force field. The Merck molecular force field MMFF is one of the most recently published force field in the literature. It is similar to MM3 but differs in focus on its application to condensed phase processes in molecular dynamics. It achieves MM3-like accuracy for small molecules and is applicable to proteins and other systems in biological significance. It is designed to be a transferable force field for pharmaceutical compounds that accurately treats conformational energetics and non-bonded interactions. This force field is adequate for both gas phase and condensed phase calculations. It uses 5 valence terms, one of which is an electrostatic term and one cross term. The internal bonded terms used in this force field are bonds, angle, stretched bond, out of plane bending and dihedral. Non-bonded terms include van der Waals and electrostatic terms. Next is the consistent force field. The consistent force field CEF was developed to yield consistent accuracy of the result for conformations, vibration spectra, strain energy and vibrational enthalpy of peptides and proteins. The CEF force field use quadratic polynomials for bond stretching and angle bending. For torsions, they use 3-time Fourier expansion. The van der Waals interactions are represented by using an inverse 9th power term for the repulsive behavior instead of the more accurate customarily 12th power term is used. There are several versions on this CFF force field. They are the Urey-Bradley version, valence version and lengthy CFF. The quantum mechanically parameterized force field was parameterized from ab initio result. These force fields use 5 to 6 valence terms, one of which is an electrostatic term, and 4 to 6 cross terms. Next is cheat. Carbohydrate hydroxyls represented by external atoms is force field designed specifically for modeling carbohydrate. Another one is driding. Driding is an all-purpose bioorganic molecular force field. It was been most widely used for large biomolecular systems. It uses 5 valence terms, one of which is an electrostatic term. The use of drying was being building with the introduction of improved methods. ECEP, empirical conformational energy program peptides, is the name for both computer program and the force field implemented in that program. This is one of the earlier peptide force field that has seen less use with the introduction of improved method. It uses 3 valence terms that are fixed, a van der Waals term and an electrostatic term. Next is EFF. Empirical force field is a force field designed just for modeling hydrocarbons. It uses 3 valence terms, no electrostatic term and 5 cross terms. Next one is GROMOS. Gordonian molecular simulation is the name of the both force field and program incorporating that force field. The GROMOS force field is the popular for predicting the dynamical motion of the molecules and bulk liquids. It is also used for modeling biomolecule. It uses 5 valence terms, one of which is an electrostatic term. Next is MOMIC. MOMIC is a force field for describing transition metal coordination compounds. It was originally parameterized to use 4 valence terms but not an electrostatic term. The metal ligand interactions consisting of both bond stretch terms only. The coordination sphere is maintained by non-bonded interactions between the ligands. Ohmic generally works reasonably well for octahedrally coordinated compounds. Next was opals. Optimized potential for liquid simulation was designed for modeling bulk liquid. It has also seen significant use in modeling the molecular dynamics of biomolecule. Opals uses 5 valence terms, one of which is an electrostatic term but no cross term. Triforce. Triforce is a force field created at Triforce Inc. for inclusion in the alchemy and Seibel programs. It is sometimes called Seibel force field. Triforce is designed for modeling organic and bioorganic molecules. It is also often used for COMFA analysis, that is a 3D QSAR technique. Triforce uses 5 valence terms, one of which is an electrostatic term. Next is UFFF. UFF stands for Universal Force Field. Although there have been a number of universal force field, meaning that they include all the elements, there are only been one accurately given at a time. This is the most promising full periodic table force field available at this time. UFF most widely used for systems containing inorganic elements. It was designed to use 4 valence terms but not an electrostatic term. UFF was originally designed to use without electrostatic term. The literature accompanying one piece of software recommended using charges obtained with this Q equilibrium method. Independent studies have found the accuracy of the result to be significantly better without charges. Another one is AT. AT is the force field designed for accurate representation of non-bonded interactions. It is the most often used for modeling interactions between biomolecules and small substrate molecule. It is not designed for molecular geometry optimization, so researchers often optimize the molecular geometry with some other force field, such as amber, then use AT to model docking process. Recent additions to AT are support to metals and solvent effect. References: Computational Chemistry, Introduction to Theory and Applications of Molecular and Quantum Mechanics, Errol Levers. Computational Chemistry and Molecular Modeling, Principles and Applications, K. Ramachandran, G. Deepa Nambudiri, and Computational Chemistry, a practical guide for applying technique to real-world problems, David C. Young, Wiley.